Today is all about modeling data with trig functions and interpreting trig functions that model data. So those are our learning objectives for today. So given a set of periodic data, model the function by hand. So I know that Excel and calculators can do it, but we're going to do it by hand. We'll use the model to calculate, and then we'll interpret predicted values and solve application problems. So, forms of sinusoidal equations. So, things like A sine B times T minus C plus D, same with cosine, are called sinusoidal equations. They're periodic functions, and they are used to model a lot of periodic data in the real world. And just a little reminder, the amplitude is the absolute value of the number sitting out front. The period is 2 pi divided by whatever number is sitting right next to the variable. The phase shift is C if you have parentheses around T minus C. The vertical shift is the plus or minus at the end. And then the max is A plus D, and the min is A minus D. So let's do a model from a table. This is the average monthly temperatures for a small town in Oregon, and we're asked specifically to let y be equal to a sine. So we're asked to model it using a sine function. So our goal is a times sine of b times t minus c plus d. And I write it down just to get into my head exactly what I'm going for. We want to round to the nearest tenth and sketch the graph, and we're going to let t equal the number of months since January. So t equals number of months since January. Now, you could have let t be equal to 1 equal January, but if I let t be equal to the number of months since January, then the first data point there is 0 and 42.5. That represents January. And we'll do one differently later. So you have to define what your t is and when it starts, what it represents. But we'll start with the easy stuff. So we can find our max and our min just by looking through the table. So looks like the smallest number is 42.5. So that's my min. My max, the biggest number I see there in my list is 69. So that means that A is equal to max minus min divided by 2. And let me grab a calculator so I can compute that. So I went ahead and plugged in 69 minus 42.5 divided by 2 and got my A. I went ahead and did 69 plus 42.5 divided by 2 and got my D. I'm going to go ahead and keep my 2 decimal places, even though the directions said that I should round to the nearest tenth. I'm going to keep it for now anyway. Then the next thing that's easy is my B, because B is equal to 2 pi divided by the period. And my period here is 12 because there's 12 months in a year. Voila. So that's all the easy stuff. Now comes the tricky part, finding the phase shift. So let's plug in what we know. Y is equal to A, 13.25, times sine of pi over 6 times t minus c, my phase shift, plus 55.75. Well, I know that this point, 042.5, has to live on my graph. So if I say 42.5 equals 13.25 sine of pi over 2 times, 0 minus c, pi over 6, not 2, times minus c plus 55.75. Then I can subtract 55.75 from each side. So minus gives me negative 13.25. And I'm going to write this as just negative pi over 6 times c. I'm going to divide both sides by 13.25 and put it on the back of the page, and I'll meet you back here short. Now, I went ahead and took advantage of the even-odd identities. I had negative pi over 6 times c, so that's the same as the negative of sine of pi over 6 c. So 1 is equal to sine of pi over 6 times c. Well, sine is equal to 1. Pi halves is equal to pi over 6 times c. Easy inverse trig equation to solve there. Divide both sides. And I get pi halves divided by pi over 6, invert and multiply, 3 is equal to c. So that's one way to do it. Another way, I think about my midline and what sine functions look like. Sine functions, if I want a positive a, are going to start at the midline and be increasing. So I look for a place that's near my midline, and my midline for this one is 55.75. So 55.75 is somewhere around April, and April is 3 months after January. So if I were just eyeballing it, I would have picked 3 as well. So I get y is equal to, and now I have to look back over here, 13.25 sine of, and my b was pi over 6 times t minus 3 plus 55.75. Now let's graph our sine function. First thing I would do is dash in a vertical line at my midline. And this is not going to be to scale, of course. Y equals 55.75. I know at 0, it's at its min, and that was 42.5 degrees in January. Then February, March, April, it hit the midline. May, June, July. Now, even though it looks like the max is in August July. It's really close. So that would be the max. We'll put that up here. And I didn't make it long enough because I'm writing too big. That's okay. I can make it longer. So here is February, March, April, May, June, July, August, September, October. So we had our max here in January, August, September, October. We're back to our midline, which is, about 55.5. November, December, and then we're back to January. We're down to our low again in January. So here, something like that, and oops, there's the pretty picture. Yeah. So minimum is in January, 12 months later, it's back to the minimum. And I did it with 1 decimal place there. And that's the pretty graph that I got off Desmos. Okay, so you practice this one. This time we're going to let t equals 1 represent January 15th. And you're going to use your model to predict the hours of daylight on September 30th. So you're going to have to figure out what input will give you the output for September 30th if t represents January 15th. That's probably the trickiest part of this one. Now, since I ran out of paper, I figured I would check in now and see how we did after having just gotten my A, my D, and my B. My max was 13.8 in June. My min was 10.5 in December. So my A and my D were easy. It's a yearly period, so B is 2 pi over 12 or pi over 6 again. Now I decided to go with cosine because if I go with cosine, I can just locate the max, and wherever the max occurs, that's going to be my phase shift. And my max occurred in June, so if 1 represents January 15th, 6 represents June 15th. So I'll just fix this. Y equals 1.65 cosine pi over 6 times t minus 6 plus 12.15. If you wanted sine instead, you would look for the place where it's crossing the midline, which is about 12.15, and it looks like that happened somewhere around March or April, so you would shift it by 3. But I like doing cosine because it's easy to find the max. Now, figure out what you have to plug in to get your prediction for September 30th. So I took a minute to logic my way through it. 1 represents January 15th, so 9 represents September 15th. So if I wanted September 30th, I need to add another half to it. So I did my function evaluated at 9.5, and it gave me about 11.7 hours, and that looks reasonable to me because September 15th I'm having 12.3 hours, and then by October 15th it's down to 11.7. To say it's at 11.6, 11.7 at the end of September. Yeah, that's reasonable. Okay, let's look at example 2. This time we're given our model. We don't have to come up with it ourselves. We're given the model for tides. The height of the tide in a small beach town is measured along a seawall. Water levels oscillate between 7 feet at low tide and 15 feet at high tide. Oh, that's my max and my min. I'm going to write that down. So my min is at low tide, it's 7 feet. My max is high tide, that is 15 feet. On a particular day, low tide occurred at 6 a.m. and high tide occurred at noon. Approximately every 12 hours the cycle repeats. That's my period. And since I know period and B are closely linked, I'm going to go ahead and write down that B is 2 pi over 12. This seems to be the theme of today. B is pi over 6. And we want to find an equation to model the water levels. So, A and D, again, are easy. A is max minus min. Minus min divided by 2 is 8 over 2 is 4. And D is 15 plus 7 over 2, which is 22 over 2, which is 11. So the main line, midline, is 11. It goes up 4 units to get to its max, down 4 units to get to its min. And we're going to let T equal hours since 6 a.m. So you have to define what your T is. And high tide was at noon. That was 6 hours later. So I have choices. I know when my high tide, my max was. I could let Y be equal to A, which is 4 times the cosine of pi over 6 times T minus, my midline happened at noon, which is 6 hours after 6 a.m. So T minus 6 plus 11. Or I know that my min happened at 6 a.m. If I wanted a minus 4 cosine pi over 6t plus 11, then I don't have to adjust it at all. Now, since I know when the maxes and mins are, I would pick the number that sits smack dab in the middle there, 3, if I wanted to use cosine or sine instead of cosine. And there's my pretty picture. Low tide occurred at 6 a.m. High tide occurred at noon. Let's see. Okay, they have the hour since midnight. Okay, so we have actually the exact same graph, except I'm using T as hours since 6 a.m. and the book used hours since midnight. And the cycle repeats every 12 hours. And you can see that this is just slightly different because I used a different starting point. If you were trying to predict the tide at a particular time, you have to think about what your starting point was, what you let your T be equal to. Okay, your turn. This is the hour hand of a clock. We have, and I'm giving you exactly, I want you to let Y be the distance from the top of the hour hand to the ceiling, X hours after noon. So X represents hours since noon. Give this one a try. How'd it go? I started by writing down some ordered pairs, just because that helped me to mentally organize the data that was given to me with all those words there. So 3 hours afternoon, it was 54 inches from the ceiling. 6 hours afternoon, it was 78 inches. That was the max. 9 hours, 54. 12 hours afternoon, at midnight, it was back to the min at 30 inches from the ceiling. Inches? Yeah, inches. Making sure I had the right units. So A was max minus min over 2. D was max plus min over 2. B was 2 pi divided by the period. And I noticed that it had a min at x equals 0, so I just decided I didn't want to phase shift at all. I made my A, my leading term, negative, and called it a day. So negative 24A cosine pi over 6 is B, no phase shift, plus the vertical shift of 54. So, interpreting periodic behavior. Most of it's pretty straightforward. Like we said, maxes and mins, how much it shifts. But we talk about the period, which is equal to the amount of time to complete one cycle. So, for example, for the clock, it took 12 hours for the hand to complete a trip around the clock face. Sometimes, instead of wanting to know how long it takes to complete a cycle, we want to know how many cycles take place in a certain amount of time. And that would be called the frequency of the event. And that's the reciprocal of the period. So, the hand completes 1/12 of a trip per hour. That's the frequency. So flip it upside down, period, reciprocal, frequency. Let's look at example 3. We're told the displacement in centimeters of a mass suspended by a spring is modeled by h of t is equal to 8 times sine of 6 pi t, where t is measured in seconds. So t in seconds. And I'm just going to go ahead and write h of t is in centimeters just to help me remember. So we want to know the amplitude and what that means in the context of the problem, period, and frequency. Well, the amplitude is 8. Which means the mass is at a max when it's 8 units above the midline. So mass moves 8 centimeters above the midline to a max, and 8 centimeters below to a min. Period is 2 pi divided by the number sitting next to t equals 1/3. That means it completes a cycle every 1/3 of a second. Frequency is 1/1/3, which is 3. That means there's 3 cycles per second. And let's see, which means completes 3, which means the mass completes 3 cycles per second. Cool. Your turn. Give this one a try. This is another mass. It just has a different function. So, my amplitude was 11. That means it moves 11 centimeters above to its max, 11 centimeters below to its min. Its period was 2 pi divided by pi over 2, and when I invert and multiply, that gives me 4 seconds to complete a cycle. So my frequency is 1/4 of a cycle per second. Get in that lab manual and work on the examples. You can do this.